So this is a great question because of how ridiculous it is. You're driving along, you're flying along at a nice cruising altitude when your pilot on the plane that you're on decides to suddenly execute a vertical loop. So you were, minding your own business, reading your phone, whatever, and things were normal, as in you felt normal. If you were just on the plane at cruising altitude, let's just say here's your seat, you're just kind of moving along at cruising altitude, you don't feel anything. This is an inertial frame of reference. We talked a little bit about those. You're sitting there reading. What you're gonna feel is basically you're gonna feel like you would feel on the surface of the Earth, which is your force of gravity is down, your normal force is up, and those two forces are equal to each other because you're not accelerating. You're going at a constant velocity, you're not accelerating one way or the other. Now suddenly the pilot executes a vertical loop, and all of a sudden the plane is telling you, your inertia is trying to do this. Your inertia is trying to keep you going at a constant speed in a straight line, but the seat of your plane is saying, no, we're not doing that, we're turning in a circle. So it actually causes this rotation. So not only does the seat have to hold you up, but it also has to spin you around. So that creates a normal force that's larger than your normal force. Now, at the bottom of the circle, you know you're accelerating towards the center of the circle, AC, which is up in this example. So what that implies when you say you're accelerating up is that your normal force is going to be much bigger than your force of gravity. Your force of gravity doesn't change in this process. It stays the same. It's just equal to mg. But what happens is you end up with a really large normal force. We talked about this in the other section when we talked about free body diagrams. Now, part one of this question, I, is saying at what speed is the plane flying at the top of the loop if the normal force of the chair acting on you is 0 at that point. So if you think about it, down here, gravity's trying to pull you down. The plane wants you to go in a circle, so the normal force has to overcome the force of gravity in order to create your acceleration up. When you're at the top of the loop, your acceleration is down because it's towards the center of the circle again, which is in this part of the problem is down. Well, you can see that gravity can actually help in this case. It can actually provide the centripetal force necessary. So in part one, what they're saying is the Fn is equal to 0. This is only true for certain circumstances, and we'll talk about it when we get to part 3, but for this part, what you want to assume is Fn equals 0. So if that's the case, then this is what we are left with. Fc equals mv squared over r. mv squared over r is equal to sum of the forces. This, let's just say, is equal to sum of the forces. In this case, the sum of the forces is just Fg, isn't it? So mv squared over r equals Fg. So then we have mv squared over r equals mg, and we can cancel our m's. So we end up with this expression, v equals the square root of g times r. So plugging in those numbers, we get 9.8 times, in this case the radius is 1,500 meters, so v equals around 121 meters per second. That's what's going on for part 1. For part 2, it's saying, now, given the fact that your speed is 121, what is that normal force at the bottom? So we're going to look at that question. So for part 2, we'll do it over here. For part 2, we look at this free body diagram. Be really careful. We like to take, over here, we sort of didn't talk about sign convention. But you see how I made Fg positive? It's a good idea to make the direction you're accelerating to be the positive direction. And it doesn't matter if it changes. Now that I'm solving part 2, I'm going to change my mind about the direction and I'm going to make up be positive. Because now the person is accelerating up. So we get mv squared over r equals the sum of the forces. And then mv squared over r equals, in this case, the sum of the forces is the normal force minus mg, right? And minus Fg, which is equal to mg. So now we can solve. It's asking us, the question is actually asking, what is the normal force at the bottom of the loop? So Fn is going to equal mv squared over r plus mg. I'll just I'm running out of space, so I'll move this over here. Fn is equal to, so then just plugging everything in. So it tells you that the person is 50 times 121 squared divided by 1500 plus 50 times 9.8. And I think what you find is that it's 978, sorry, 978 newtons is the normal force at the bottom. Okay,